Welcome everyone to this session. My name is Rolf Leutert from Leutert Net Services, Switzerland. As you easily probably will hear my accent, and you may have to get used that I pronounce some words a little bit different. My own coding for this. I would like to present you some selected topics about IPv6. Unfortunately, I have only 1 hour and 50 minutes. I thought I would like to have 2 days for this topic, but we're here to get an overview, and I try to do my best. I hope everybody has already some information about the topic, because I will not have the time to tell you all about the address, new address format and everything. What I would like to pick out is some very interesting things which have dynamics. There are different ways of getting introduced to IPv6. Either you just don't do anything and let it happen, but then you wouldn't be here. The second would be you buy a book and read through the protocol book. That's a very hard way of doing it. Or my preferred way is you take Wireshark and discover what's happening. Because studying a protocol with a book is a very hard job. A protocol is a dynamic process, a dynamic flow of process, a step of process, and a book can hardly describe this. It's good to have the theory in the background. You need the theory, and I will provide you with only a little theory for the time reason. But at the end, to really find out how it works, you need to have a tool like Wireshark. Wireshark is the best tool for it. It decodes all the IPv6 frames and formats we will see here. So let's go on. And here are the topics which I picked out, as I said, out of the 2 days training which we normally do. We start with the auto-address configuration. Everybody has heard of this. That's a very different story. It also already offers a lot of variety of implementation, because many of these processes are actually running on the workstations. And as you know, there are lots of different workstations out there. And an XP does not behave the same like a Mac or Linux. So we have to get used that there is much more happening on the workstation side. That's the first message on IPv6. Before, in IPv4, we had more or less 2 choices on the client side: manual configuration or auto configuration via DHCP. Now we will see we have much more ways of configuration, and that's one of the topics here in the host configuration with DHCP. Diversity configuration will be our first topic. I'm sure you heard of it. Neighbor discovery, router discovery, that's a brand new stuff. We didn't have this before. I'm sure you heard that we do not have any broadcast anymore in IPv6, nor on layer 3, nor on layer 2. So with the Ethernet destination, the all Fs is gone. You will never see it again. And in the IP level, the 255 at the end of the IP address is gone too. You remember that was a subnet broadcast to reach all stations in one specific subnet. That's gone. We don't have this anymore. Instead, we have neighbor discovery and router discovery process, so we do not have the ARP anymore. The address resolution protocol is gone. So it's very different here, and we will cover this again looking at trace files. The DHCP I mentioned already. The DHCP is still there. It works in one version same as in v4, but we have a more granular way of using DHCP, and that's also some word. So the transition technology, that's again something which of course is new. That's something we use only. because we will have coexistence of IPv4 and IPv6 for many years. People are talking about 5 or 10 years where both network stacks will coexist, which allows us to smoothly move forward, which is okay, but there will be also some very demanding topic on that. We are talking about tunneling or transition. Again, I cannot cover here all of them. There are more like 6-to-4, 6 RD, rapid deployment and all this stuff, but I have to pick out here some topics. So let's go back to the auto configuration SLAAC, SLAAC, which is implemented in any IPv6 client. So independent of what operating system you have, as soon as you turn on the IPv6 stack, either by a command line or by a tick, the client itself forms something which is very new. It's called a link local address. We didn't have this before. It's an address which is valid in the subnet only. You cannot leave your subnet with this address. Link local means the subnet. It's another word for subnet. So you can cross routers, not routers, you can cross switches, hubs and all this layer 2 stuff, but a router will never forward an FE80 address. So that's the first pattern you must memorize. FE80, that's a very important address. It's a link local address. Every client turning on V6 will form a link local address, and now, in addition, per interface. So you will have a link local address on the Bluetooth, on the wireless, on the Ethernet, and so on. As many interfaces as you will have a different FE80 address, but it will start with FE80, so the first 64 bits. And remember that in IPv6, the first 64 bits are the network, the prefix, and the last 64 bits are the so-called interface identifier, which used to be the host part. So here we have something which is easier. You will rarely move what has been called the subnet mask. So the standard, all the addresses still have a standard mask, and it's actually /64. That means the first 64 bits will be the network prefix, and the last the most right 64 bits will be the interface identifier. So there are two ways for the client to form the interface identifier. One is shown here, and I'm sure you have heard before. It's called the EUY64 because it actually derived from the MAC address of the appropriate interface. So it takes the MAC address from the Bluetooth or from the wireless or whatever, and takes a very specific scheme here. It actually inserts the FFFE here in between, and it makes this byte here a 02, which actually stands for local administered. You have to know this. But you always will see the MAC address of the interface hidden in this address. So this is one way of doing it. It's called EUY64. The other is called privacy, because there has been concern, as soon as this method has been defined, there has been concern, but I can trace then my client because I may know the MAC address, so I can trace the client from the IP address. So there was also defined another method called privacy, where the 64 bits are just random selected. And you even can choose the interval where this random will change. Remember, this is FE80. So first you must define which method is used on your client. And again, you will see this very easily with Wireshark, because when a client forms this address, the first thing he does, he verifies that this address is unique on the network. So we will see this address on the network. And as soon as you see an FF, FE inside, and I will ask you later on what address it is, as soon as you see an FFFE, then it's probably an AUI address. Later on, again, back to this. Again, with this address, the client is not able to leave the subnet, but he can talk to local clients on the same subnet. He even can talk to the local router on the subnet, on the interface. And when we later look at the configuration for the so-called default gateway, which everybody knows, we had it in IPv4 already, then we will be surprised that in this field there will be an FE80 address, the one of the router, because the router must be reachable locally. And it even goes any further. For those of you who configure routers, interconnection between routers, we used to have a /30 network. We don't use this anymore if you don't want. You don't have to configure anything on link, point-to-point link, because they just grab the FE80 address of the appropriate interface. So completely new options and possibilities here. But again, this prefix is not routed, is not routable. Not even in your internal network, a router will not forward this frame. So what we need for is a valid prefix. We need a valid prefix. A valid prefix can be configured manually. I recommend you never do this, because configuring manually here is hard work. Because you have a lot of typing error probability. So what you normally do is the prefix is provided either by the router, that's new, or by DHCP server. So the router has a new role. The router in a subnet can provide the client with the prefix of that network. And we will see this again in a trace. So again, when the client receives a prefix here, that's a prefix from the router. And remember, that's the second pattern you have to remember. Whenever a prefix network starts with 2, it's a global routable unicast. So if you take your quick reference card and go to the very first page of the front page, you will see a collection of these different addresses, of the different writing. You also see, for those who never saw it, the suppressing of local, of reading 0, and so on. That's all stuff which is, of course, needed to know, but I will not cover here. But if you go down, you see the FE80 is linked local. If you see 2000 is our global assigned addresses, unicasts. That are the ones which you get from your registry, ARINC, or whoever is responsible for your area. So here in this case I just took a random pattern. This is a so-called reserved for documentation. So this is a range which cannot be used on the internet. It's for documentation 0db8, but there are plenty of possibilities. So our client does the same procedure again. Whenever it receives a prefix, he either takes the EUI format for the rest or the random format. And again, it's hard to say which version is preferred. It depends on your operating system. For example, the Windows Vista, Windows 7, they prefer the privacy. But this was not all the time. You can switch it off and on with net-shell commands. So it's a whole list of operating system on the internet which way is preferred. Can the random privacy format have the FFFE in the middle, or is that excluded? That's a good question. Can we have FFFE here in the middle? The answer is probably yes. I never checked it. It's a huge range. It's a 2 to the power of 64, though the chance is very small. Anyway, it wouldn't harm anything if it is. It just would mislead you by assuming it's AOE, but it wouldn't harm any function. Okay. Good question. could EFF also happen here? I guess yes. I didn't find an answer on the internet. Anyway, the O2 must be then here also, right? To have a really, the O2 should be there and also.
Oh, okay, I was wondering.
Because the O2 is also part of this AUE. Okay, at this point the client has an FE80 address, link local, and the global unicast. And he still keeps the FE80. The FE80 is never lost. The FE80 is there as soon as you start the step. And now, the most strange thing is that's not enough. The client has a link local address, he has a global unicast, but now something very different from IPv4. I called it the most strange thing. Every client now forms its own multicast address. So let's go step by step. Let's say you want to reach this station here. So you are not this station, but you want to reach this station. This is an IP address. So you either type in telnet and then the IP address and go. You probably won't do. You probably resolve the name through DNS anyway. Whatever you do is, there is a frame going out to this destination. But before you can send out the frame to an IP address, you have to resolve the hardware address, right? Because you have to form a proper Ethernet frame. And the Ethernet frame has a destination, 48-bit field at the very beginning. You have the IP address, but not the MAC address. And for that purpose, we used to have the ARP, which was sending out the broadcast all over the network. Who has this IP address? But the broadcast is forbidden. And what we do is, we are looking for that station with a unicast. What we do is, we take the last 3 bytes from the address, 6B, 8532, independent, whether it's an EUI or a REN. We just take the last 3 bytes, copy these bytes in a prefix which is given, /104. You see, this is 104 bits plus 24 gives 128. So this is so-called SNMA pattern. SNMA solicited node multicast address. So we are actually sending out the frame which discovers this station. We are sending out the frame to this address, FA02. So this is a third pattern you have to emphasize. Actually, the pattern is longer. You remember 2 columns in a row means that you can fill in all the zeros here. All these zeros they are represented by these 2 columns here. And remember that always 2 bytes are separated with a column. Again, that's theory which you can read in the book. So we are sending actually a frame out to this address. And now what happens is the station itself will react to this multicast. So it will reply with its MAC address. And that's the amazing thing, because every station which has an address forms it for his own purpose, his own SNMA address. But he will never use this address actively. It will only be used for somebody looking for him. Again, if you read this in the book, after 2 pages, you forget it, right? You will never understand how it works. I will show it to you with the trace file, and everything will become clear. So now we are ready to look in the first trace file. We have all we need. The first trace file we are going to open, and you have it on the chart, the stick located, running around. It's called IPv6 Neighbor Discovery 01. And of course I have it ready here for you. What I did here is actually, I did a special profile here for IPv6. You know, that's recommended. You do a new profile just by going to edit and configuration profile and give him a name. By the way, on the stick which is circling around, there is also a so-called color profile on, so you can import this color if you want. very easily just by going here to edit coloring and then import from the stick. And it will add at the end of your coloring rule, it will add some very specific V6 coloring. So this makes it a little bit more readable. So let's go back to our first view. So we have again some special writing here. So we see here in the source field a column and two columns. And that's again a special writing. It represents IP address with all zeros. You remember that in the IPv6 you can replace all the zeros. What if the address has only zeros? Then this is the writing. So this address is an all zero as a source. Let's verify it. Let's go into these details here and go to the source field. And you will see that actually if you go down here, all the bits 128 bits are 0, and this is how you write it. So this is a frame with the source all 0. It's actually called the duplicate address detection. It's called the duplicate address detection. When we talked about the process of random forming an address, one must be sure that this address by chance does not already exist on the network, right? Only valid for the subnet, because for the same subnet, because the other subnet will have another prefix. So this address must only be unique in the local subnet. What actually is happening here in frame number 1 is this duplicate address detection after link local auto configuration. And here you see for the first time this strange SNMA address, FF02, and then you see here this strange address called SNMA. Another word about the multicast address. Again, a completely new use of multicast is also written on your quick reference. If you go down to multicast, you see they always start with FF. FF means that this is a multicast, we don't have any broadcast, so this is multicast address. What is new is that with the second byte in the multicast, the sender can define the scope, the reachability of a multicast. That's very interesting. It will be, I think, it will be used a lot. For example, if you send a frame to FF01, you won't even see it on the wire because it's like a local, in the machine, like the loopback, right? If you see it on the, if you see FF02, that means this multicast should not leave our subnet. It's a link local multicast, which is okay for verifying that the address does not exist, right? Because it can only exist on our local network. With the F05, you can even say our multicast reaches the whole enterprise network. So that's very new, and I think there's a lot of potential of a lot of applications for this, for streaming and things like this. You, as a sender of a frame, can define the reachability of a multicast. So the sender, which was sending out this frame here, was actually telling this frame should only be in the local network. So here you see that this address is now checked on the network. So the client is looking for its own address on the network, and he hopes or expects that nobody replies to this, right? Because if somebody will reply, it would mean somebody already has this IP address. Which should not happen if we are using EY, because the MAC address should be unique anyway. It could happen if we use random, but the chance is very small. 2 to the power 64 gives something with 18 zeros in there, but it's there. So this process happens anyway. Whatever the client is using, either EUI or random, this dead happens anyway. So it verifies the address on the network. So now we are having a unique FE80. If we go into the detail of the address, let me check here. If you go into detail, you will see that he will verify his own address here, FE80. That's the full address which he now has formed. My question now to you, did this client use the privacy or did it use the EUI method?
EUI.
Who is for EUI?
EUI.
Who is for privacy? Who doesn't care? Okay, yes, you're right. It's actually the AV format. You can see it here from the FF02, FFFE, and here you actually have the 02 at the beginning, but remember the leading 0 has been dropped. So this station here, well, now, if we say it's EUI, then we should find the log 3 bytes in the MAC address. Let's verify. So we close this for a minute and we go up to the IP MAC address. And in fact, the log 3 bytes 6B8532 are the log 3 bytes of the IP address. So that's very new. That didn't happen before, not in IP, that we take part of the MAC address into the IP address. Okay, let's go on here. For time reasons, I must go on here with that. We're coming back to this process, to this trace file in a minute. So what also, again, I mentioned is different, that every interface in a notebook or in a PC gets IPv6 address. Here you see a list, Bluetooth, the Wi-Fi, the hardware gigabit, and even more, we have a loopback interface, that's new, and we also have so-called virtual interface. We will talk about two of them, the Teredo tunnel and the ISATAP. And the interface, they have a so-called zone ID. So that's important later on when we use command. You may use this zone ID, that's the interface adapter. Sometimes you have to tell your machine through which interface a command has to leave. And then you need the zone ID, which is listed here at the end of your command. Yes?
If you're using auto configuration,
yes,
and it auto configures your router interfaces.
Your what interfaces?
The
your
router.
Router?
The routing.
No, you don't use auto configuration on the router normally.
Doesn't it globally?
On the router side, you can, but it's not recommended.
That's what I was getting
I'm
at.
talking about user client here.
Okay, that's what I needed to know.
I'll come back to the router story. Okay, so what we see here is that we have on some interfaces we have a link local address and a global address. Let's quickly go back and look what interface is 13. Interface 13 is obviously our gigabit interface. So on the gigabit we also have a public address here. So this means there must have been a router around which gives us this prefix. I just for curiosity selected the name cafe because we have hex now. You can write whatever you want, right? This is not a valid address anyway. You can do beef or Facebook, for example. They wrote Facebook with 0, things like this. So this is a global unicast address. With this address, the client can reach, access the internet. And you can easily see that each interface has now a link local address, 13, but some interfaces also have a global. For example, the 16, let's go back, what is the 16? The 16 is the ISATAP and the Teredo and so on. So we have to get used that the client has many interfaces. And some of them have a global, some of them have only the link local. But all the interfaces have the link local. You can try it. As soon as you connect the interfaces, of course it must be connected, either a cable or a wireless network, not on dead interfaces. If the interface is shut down, then there is no address. Okay, now we have an address, but we cannot talk to anybody yet. We have verified that the address is unique on the network, but we don't have a neighbor, an address from a neighbor available. So let's see how is happening here. This is a chart which shows what will going to be happen over the next 5 to 10 years. Many machines, servers, clients will have dual stack. That means beside the IPv4, which is already running, we install a second family of protocols. Actually, TCP and UDP are the same, no changes on these headers, but they must be accessible through from the application. What also has been taken over is the ICMP, Internet Control Message Protocol. This was a protocol for networkers only in v4. It's used for PIN, it's used for error messages, destination not reachable, packet to bit. That's all okay, and it's still present in IPv6. But IPv6 plays a much more important role than v4, because the neighbor discovery, the router discovery, and even the multicasting, it's all given to IPv6. That's why the next slide zooms into this red area only. So this was the group which we had before, error message and control message. We don't cover that. New, we are replacing a protocol called IGMP, which has been used for broadcasting. The broadcasting is where multiple clients assign to a transmission, video transmission. We don't cover that for time reasons. What is the third group, and that's what we are going to talk about, is the neighbor discovery messages, ND. There are actually 4 messages which we are going to look at: neighbor solicitation, advertisement, router solicitation, advertisement. So they are actually on top of IPv6. So we go back to our trace file here. You can do this live if you have the trace file, or just look at this here. So after our duplicate address test detection has been done, our client, and here you see the client again, is sending out a frame. Let's quickly adjust our resize our columns. He sends actually out a frame called router solicitation. That's again new. So far, the client didn't know that the router exists. He had no idea about the router. But here it actually sends a router solicitation. And everybody can tell me now to whom he addresses this packet. Just take your quick reference, and you can even tell how far this packet will travel. Will it leave the subnet? No. To whom it is addressed? To? What is the address? Yes? All routers. The client has not a clue if a router is existing in the network, right? It must not be. You can pull it on an empty switch, but it tries if there is a router. What does he probably want from the router? Anybody has carefully listened to me, he should know the answer. What does he probably want? What parameter, what value he wants from the router?
He wants an advertisement.
Right?
He wants a router advertisement.
Yes, he wants actually a valid prefix, a global prefix. He gets this from the router, but only if a router exists. Right? So, that's anybody knowing about Wireshark analyzing. Do you think in this trace a router is available in this area? Is there a router available? What do you say? Who is for yes? Yes. Looking at the next frame, looks like a reply, right? It's a router solicitation. So what would you expect to find in the contents field of the next frame?
To all nodes. Well, to that node. And advertiser sign.
See here? So the router provides the client with the prefix. of that network. The router, of course, must know the prefix of a network, right? Otherwise it cannot do the job. The router must know a prefix on every interface. Why not using this information and give it to the client? So you do not need to configure the client anymore with DHCP. As soon as you plug it in, he sends out the route solicitation, and if a router is present, he gets an advertisement with the prefix.
So
yes?
that's merely that comes from the router merely by turning on IPv6?
Yes.
That's it?
You turn on IPv6 and you configure this prefix on an interface.
Part 2 is you manually configure it?
On the router you manually configure.
Thank you.
Yes. On the router you must configure a network. But that's nothing different from v4, right?
No.
That's exactly how you configure a v4 router. You configure a subnet 10.10.20 on a subnet on interface 0 and another one on interface 1 and so on. So it's the same job as on a v4 router. You must configure a network. So here, looks like subnet 20, right? The next may be subnet 30, subnet 40 or so. Yes?
So you would configure your router first before you plugged in your client?
If you do not configure the router, then there will be no reply on frame number 2. Frame number 2 you will still go out. And you will see frame number 2 if you capture on your home. If you just turn on IPv6 on your Windows or on your Mac or on your Linux, you will see frame number 1 and 2. But no reply. As long as the router is not configured, yes?
How does the router know this number?
The router knows...
the global number. Global.
You must configure it on the router interface.
But how do you make sure it's unique, globally unique?
If a router has on the same router have the same interface twice, it will refuse his job. A router can only work, it have on each interface a different IP address. That's prerequisite for a router. Otherwise it will not do his job. Yes?
What happens if there's more than one router?
Good question. What happens if it's more than one router? You will get more than one router advertisement back. And that also replaces hot standby protocols, because you already have 2 routers. And hopefully, what do you think about the prefix in the 2 announcements? What should be given? It probably should be the same, right? Otherwise, you made a configuration error. If you have 2 routers with each allowing the same subnet, you should give these 2 routers the same prefix. Otherwise, you mess your network up completely. You can do as many routers as you have in the same subnet. But they must all have the same prefix, otherwise they do not agree, and then you may produce routing loops and all the consequences which may have. So you can have more router advertising, just finishing, and other than in IPv6, if you have more than one router, the client will take both routers in his list. So if one router is not available anymore, he just will take the other one. That's what we did before with hot standby routing protocol. The protocol which we have a standby and active router. It's not needed anymore. You just add another router and the router. Yeah, another question?
I've heard a couple of times now that you can apply more than one IP address, v6, to an interface also.
Yes,
is that
yes.
true? Why would I do that?
That's big question. Why would you? The question is, I could apply more than one prefix on a subnet on the same interface. And that's what I actually did. And I have trace files here available. I actually configured 2 routers with different prefixes on the same internet, on the same interface. So what the client actually does, it has an address from each router. It has 2 prefixes, and it's then more or less random which one he is using. So we have to get used that the client can have 5, 6 different addresses. But at this point, we cannot say what will be the purpose of it. What can it be used for? But the possibility is there. If we are ever going to use it That's another question. But that's always with a new protocol. The engineers build a lot of function in because they would like to last this protocol for a long time, right? IPv4 was here for 30 years. That's a very good job. What do we have here still active since 30 years? Nothing, right? IPv4 was really good design. The same is for IPv6. They try to put in things which makes protocol very flexible for the future. And one thing is that the client can have as many addresses as he wants. Yes?
Sir, for when it gets the randomized string from both routers, will the client pick which address it's going to take?
The randomized string is not part of the router advertisement.
Okay.
It's only the prefix. If you go up, then you see the prefix length 64. So the client from the router only gets the first 64, which is called the network part. The rest of the 64 is either randomized or EUI, and that's a decision of the client.
Oh, okay.
Okay? That's important that everybody got this. You even can influence how the client is doing it. I have put the most important netshell commands on your quick references. If you go to the back, there are plenty of them in the network, so I didn't put them all. But if you see a command like netshell interface IPv6 set global randomized identifier disabled. A nice, easy to remember command, right? So you can tell the client how to behave. Shall he use privacy or shall he use the EUI? But you must look first, what operating system do I have, because the default values are different. I think on the iPhone, they just recently changed default to privacy from EUI. So the default may be different, right?
If you're configuring the router interface and you do like multi-netting or two IP, global IP addresses on it, will it end up, will the EUI or the IP network ID be the same?
Only if you're using EUI. If you're using privacy, it will be different. If you're using EUI, then we would have the same prefix with the same EUI. The question was if we have more than one prefix, would be the interface identifier the same? And the answer is yes with EUI.
What happens if it's not unique? If the self-configuration address is not unique?
What happens if
it's not unique?
If it's not unique, if it's a MAC address, then it's very rarely, right? If it's EUE, then it just, if it's privacy, it just turns again the wheel and takes another address. If it's with EUE, then it should not be existent, because that would mean that you have the same MAC address on your subnet, and then you cannot work anyway, because then the switches get confused, right? They start swapping over, and then they will even block ports at one time. So yes, the question is should be solved. Okay, we should go further. I know there are a lot of details in it, but let's go further and see what happens now. So let's go back here with this. I didn't show you all here. Yes. So an interesting detail, and no books, I didn't see any information. That's again something you can only find out with a Wireshark. What would you expect if you send something on a solicitation? What would you expect the answer is sent to? You would expect that the answer is sent to the one which was asking, right? This is not the case for the router advertisement. To whom is the router advertisement sent?
All nodes.
All nodes. Another multicast address, you see? To all nodes. So these are all the small little things. You could spend hours on the internet to get the wrong answer. Or to get many answers. And you do a 5-minute or a 10-minute and you have the answer. The advertisement actually is not going back to the one requested, it's going to all. Why this? I don't know, I can only speculate. The router advertisements, they are sent out anyway in a certain interval. So this is just used to inform again all about the network. So the interval is re-triggered if somebody is requesting, right? So we save we save actually one announcement, because the prefix has a valid lifetime. So we cannot use the prefix for forever. In the prefix announcement, there is also a valid lifetime. If you go into it, again, I told you there are much details here. So you must repeat your announcement. So here you see a lifetime of this announcement. So whenever you repeat the announcement, so these are the small details you can see here. And let's do another last. Can anybody tell me what this packet is here? Frame number 4. Can anybody tell me what is this packet here? What is this packet? It's actually a neighbor solicitation. So we remember that neighbor solicitation are used instead of ARPs. What is this kind of address here? What kind of address is this here? SNMA, right? It's an SNMA address, starting with FF02, column 1, FF. So the last 3 bytes are actually part of the IP address we are looking for. And what our station actually is looking for here is for the router. He's looking for the MAC address for the router. He has received the announcement from the router, and now he is looking for the router MAC address. So in the next frame, we should see the MAC address of the router. If you go down here, you can see the MAC address of the router. And now, what the client does, he does an entry in the neighbor table. We don't have an ARP table anymore. It's called neighbor table. It works similar like the ARP table, but as I mentioned, not using broadcast, multicast instead. So now we are ready. Our client has now a prefix, a valid prefix. He has a default gateway address. He has a valid address, a valid mask. There is one important parameter missing. A client has an IP address, he has a default gateway, and he has a mask. What other important parameter do you normally need? Anybody has an idea? DNS. The gateway we have, that's the router. We just did a resolution here. We do not have the DNS. Okay, we can work without DNS, right? It's just hard. If you want to enter IP address in browser, okay. IPv4 is okay, but we try it with IPv6. Forget it. Okay, so we need another parameter for the client. Sorry. And that's the next topic. And there's a big discussion. Am I in time? Okay. Too late already. So a big discussion. Why do we need DHCP? Why can our router not provide the DNS at the same time? And I guess I was I'm visiting the huge conference in Germany, Frankfurt every year, IPv6 conference, and we can expect that the protocol is not finished V6. We can expect that there may be a possibility that the router not only delivers the prefix, that it may also deliver the DNS IP address. And this would mean that for small enterprises, we do not need the DHCP service anymore, because that's actually all a simple client needs, right? I'm not talking about VoIP telephones, which need much more parameters, but the simple, normal, standard client would be happy with this parameter. It's not implemented at the moment. We cannot deliver DNS through the router. And it will not be an issue, it will not be a requirement for huge enterprises, because you do not want to configure the DNS on each router interface, right? But for a small enterprise, that would be a solution. So it's not supported, but what is supported is, I mentioned it already, we have more granularity in the DHCP, in the use of DHCP. And the good message is, for the networkers amongst you, we gain more control above the client back to the network. We can now say how the client should behave. We can tell the client whether he should contact the DHCP or not. That was no way in IPv4, right? In IPv4, you had to configure on the client itself, manually configured or DHCP. That's gone. You can control it through the router just by small little bits and small little commands on the router interface. And that's what I would like to show you here. And again, you will see trace files which explains this very clear. So we have actually three possibilities here, and I'll explain what it means. The client, he needs a subnet, prefix, and a mask. That's what we just realized he gets from the router advertisement. The interface identifier is auto-configured, either EUI or privacy. That depends on the client. DNS is either manually or it takes the V4. Maybe it has, again, remember that the client normally has a valid IPv4. And he could use the IPv4 DNS to contact the DNS. So this would work. So this is one way of working. But you can then, in the router advertisement, you can set a so-called other flag. This is a command on the router interface to set this command. What does it mean? In the router advertisement, beside the prefix, there is another flag, which means it tells the client that it should get other parameters from the DHCP server. That means the client still takes the subnet prefix and the masks from the advertisement. He still makes the interface identifier with one of the two techniques, AV or privacy, but then he sends out the request to a possible existent DHCP server. So we force the client to do this, and we can ask him to do this. And now is the point where first client like XP, they don't care anymore. They don't look at this bit. So here, I told you already, we must be aware that we will have a different behavior on the client side. And here it starts. The XP will not look for a DHCP server, independent whether the bit is set or not set in the announcement. So this works for Windows Vista and Windows 7 upwards only. And then we have the third possibility. Beside the other flag, we will also set the managed flag. And this means that the client gets fully configuration from the server. And now we are back to what we had with IPv4. If you would like to know what IP address the server has, including the interface identifier, then this is the way of doing it. But then you're back to what we had in IPv4. You must configure ranges on the server, from here to here, right? And you must care that the ranges do not overflow and that the lease time and all these problems. But you can do it. And I realize that a lot of people prefer this. They are not aware of the new possibilities. On the other hand, it's very difficult if you have firewalls and you assign rights to a specific IP address. How do you handle that you have a privacy address and the client changes the address every hour? I don't know any firewall being able of handling this, right, at this point. So, again, I'm explaining here to you all the possibilities. I'm not telling this is the way to go, because that's not clear now at this point. I'm just telling these are all the possibilities. An interface can have 10 IP addresses. Is it useful or useless? We don't know, but it can have. So please take just note. We cannot say this is the way to go. We just can say that's what is offered now, and that's what may be used or maybe not used. So let's look now at another trace file. It's called DHCP IPv6 DHCP 01. So I quickly open a new file here, and we see the same thing as before. But before we didn't see here these nice pink frames here. So somebody must have changed the behavior of the client. Because if you see here, the client is now, after he received the router advertisement and after he solicited the router MAC address, he is sending out a new frame and it's called information request. And again, take up your quick reference and tell me, is this a meaningful address here? Does this address make sense? FF02, column 1, column 2?
Sure.
Yes.
Yes, it makes sense.
It could be octets of zeros and leading zeros in the last two octets.
Yes, that's the writing noting, but is it also meaningful from the contents? You don't have the quick reference, that's why you cannot help us. Oh, you have, okay. Is it a meaningful address?
DHCP relay agent.
Yes, DHCP relay agent, right? What is a DHCP relay agent? A relay agent is a router which has on its specific interface configured a relay address. That's again a manual configuration task. It was called helper address in the V4. So only a router which has on an interface this command configured will pick up this packet. And what will he do with the packet? He will send it to a DHCP server. It can be anywhere in the network, because you have to configure the address of the DHCP server on that interface command. So what this router actually does, it picks up these frames and envelopes it in a unicast frame, and then sends it through the network to the DHCP server, the same as we had in V4. And here is another myth you can read on the internet. I have seen a rare story that every router now on the way to the DHCP envelopes this frame. Absolutely crazy. Only the first router is doing it. And afterwards, after the first router, it's not a multicast anymore. It's a unicast to a dedicated destination. Why should a router envelope this? It's useless. So you do one trace and you find out that this is shit. This is that this is not true. It's just not. It's just wrong. I can show you a trace afterwards. It has been taken after the first router. It's just a normal unicast. It has the source of the router and the destination of the DHCP. So no need for all the following router to do something with the packet rather than forwarding to the right network, right? So there's a lot of nonsense. I always say packets don't lie. Everything else you cannot trust. Packets don't lie. Trust the packets. So if you're not sure how it really works, do it with Wireshark. So let's go back to our last advertisement and verify that this bit has been set here. So if my theory is right, and I just told you don't believe anything without seeing it, if my theory is right, that this frame here is an action from here, then here in this router advertisement, which flag should be set? Can anybody remember which flag? The other flag. Let's try, let's look here at the flags. Here we go. Sorry. Let's go into the flags here, and you see here, oh, like the other flag is set. And this means to the client, you will get other parameters, like a DNS, from a DHCP server. And that's what the client then does. He sends out this request. Inside the request, he will even state what parameter he wants. Depends on the client. As I said, a web telephone would ask for VLAN number and things like this. A normal client would ask for a DNS server and for a domain search list and maybe for some specific information. That's what the client is asking for. Let's see if he gets all these options. It must be in the reply. Here we go down. Actually, he receives the domain server, he receives the search list, and he receives, of course, the IP address of the server. Of course, it's an IPv6 address. Let me see. Here it is. It's actually cafe. That's the short writing. That's the IP address of the DNS server. Now the client has everything he needs, but with the involvement of the DHCP server. And as I mentioned, this is a discussion. Do we really need just for this? Do we really need the involvement and the setup of a DHCP server? So keep an eye what's going on here. That may change in the future. So don't. Sorry. A little bit too many windows open here. So okay. And here, if you don't trust what I said before, after the first router, it's not a multicast anymore. So this is a screenshot of made after the first router, and you see here there's no multicast anymore. It's the source address of the router, and it's the destination address of the DHCP server. And here the answer comes back. So no need for any following router if there are to again wrap this packet. It's a pure routeful v6 packet which you see here after the first router. So the router here has the helper address or the relay address configured on that interface only. And here he picks up then this request which we just seen to the one column 2 at the end to the helper. Okay, so that's no rocket science. It's kind of similar like we had it in v4, but still you need to realize. And now our client is ready to go. It has on a specific interface, it has a link local address, it has a global unicast address. Again, you see the FFFE, so this is the EUI process. He has a standard gateway. Look at this. The standard gateway is an FE80 address. So this is gateway. FE80 is okay because the router is reachable through the local network. So that's new. So far we had here in this field, we had the valid IP address of the router. And this router has a valid IP address, but there is no need for the client to learn it, because he can use the link local address of the router, because the router interface is in the same subnet. Now let's go back to our drawing here. So the client here learns the FE80 address of this interface here. And that's where is sending all the frames which are destined for outside the network. That's not been changed to v4. Yes.
What's that %13 on the end?
Yes, good question. What's that percent on here? That's a good question. Remember before when I said that sometimes you need to specify through which interface you must send out a packet. And remember that every interface has an FE80 address. So if you make a ping to an FE80 address, how should the client know through which interface he should send out this packet? So he must, and this is done automatically, he must note, I learned this default router through the interface 13, which in this case is Ethernet. He could have the same for interface 16, which is the wireless, but then it would be a different FE80 address. So very good here, this %13, this is the interface ID of the Ethernet. And here then the DNS, that's the value he has received through the DHCP server. Any more questions on this?
Yeah. Would that be distinctive within a lag as well, in an aggregated?
Say again?
Would you use that %13, 14, 15 in a lag to distinctively separate or load balance in a link aggregation group or something like that?
Yeah. The question is if you're using this interface, interface ID also if you have more than one address.
Right.
Yes. Yes, you would have, as long as it is an F80 address, you need to have the percentage at the end. Because FE80 addresses are not clear, distinctive, yes. Okay. So, this is what you can see at your, easily see at your home, at your local network. Of course, you need to have a router configured with a V6 address. But what you can do without the router are the following techniques. That's why I would like to spend the rest 10 minutes for the most complex thing of this session. It's tunneling. Tunneling is don't talk to firewall people about tunneling, right? They hate it. They will hate you because tunneling is a method of drilling holes into walls and security issues and kind of smuggling information through it. But we have to do it because it will last a long time until all providers will have an IPv6 backbone, because they will have invest million to, and will take years. So what we do with tunneling is we make use of the existing v4 infrastructure, but inside a v4 packet we have a v6 packet. And that's really a nice way of starting with tests. For example, ISOTAP is a Microsoft term for it. There is some other technique called Mirido on Linux side. Is something which you can easily test on a v4 infrastructure. So you have two v4 networks here, network 20 and 30. Your intranet enterprise router, he has not a clue about v6, but still you can ping v6 from here to here. If this client is dual stack enabled and this server is dual stack enabled. So what you use what you're using here is the so-called ISOTAP interface. And I mentioned it already. ISOTAP is one of the logical interface which is formed as soon as you turn on the v6 stack. But what it actually does, it takes a strange way of forming a v6 address out of your existing v4 address. So you must have a running v4 stack. And what it actually does, it takes the last 4 bytes and forms a very typical IP address. It starts all the way with FE80 and then the very specific 5EFE. You can even see it on your list here on the last page about tunneling. What kind of address is this, F80? Link local. So how far you would normally be able to reach to talk with this address?
One hop.
One hop. One to the one hop or over the next hop?
Just to the...
Just two.
Yeah.
Okay. Yes. So this router would normally not pass this, but this router does not know anything about v6, and because we are tunneling, we can actually reach this guy over here with the FA80 address. So you can set up a ping to this guy here. Ping FE80, 5EFE, blah blah blah. But then don't forget the percentage of your ISOTAP interface on your side, right? Because you must tell your client, this ping must go out the ISOTAP interface. And here again you need this percent, right? And what happens? You can try it within 5 minutes. Just take 2 stations, turn them to v6 and ping them over. You can even do it in the same subnet, but that's not so funny, right? It's funny through a v4 router. So what actually happens is a tunnel is immediately end-to-end. The tunnel starts here and it ends here. So and it looks, and you go to your interface and you see immediately that you have an ISOTAP address. You may have to activate with netshell command, you may have to activate the ISOTAP interface, which you can find on the internet. As soon as you activate the ISOTAP interface, you have this address here. It is derived from the IPv4 address and is valid. But remember, if you ping, you must add your local ID of your ISOTAP interface, which is not visible here, but visible on the list. And it works. And the trace file looks like this. You can, I open it quickly. Another 5 minutes, okay. And now I have even another profile, because now you see that inside this V6 we have a V4 address. See here? And now I made another profile. It's called tunnel, V6 tunnel. I can select it by pressing down here. New feature that you can access the profiles directly from here. So what I did on this profile, I actually made the 2 more columns showing the IPv4 address and the IPv6 address. And now you see that these packets here, they will of course pass the V4 routers, because it has not an idea, it does not need to know that inside there is actually V6. So you have a V4 header here, and then you have a V6 header. But the end station, the server which you ping, he unpacks the packet to V4 first, and he realizes there is another header, and then it again unpacks from the V6. So if you get a reply, ping reply, then you can be sure that your destination is V6. So here you see echo request and echo reply.
So in this migration, you would touch all of the clients, but not the core.
Yes. You can start with one client and one server, and it will work. You must not touch all the clients, just one client.
So, and migrate client by client.
Yes. Yes.
But you still got to mess with the core eventually.
The core must not know anything about it. The core is still running at V4. Route. Because the packet has a valid V4 source of this guy and destination of that guy. Yes.
So you're saying that there's essentially, in this scenario, there's no IPv4 hardware in the middle that will cause this to not...
IPv6 hardware.
No, but I'm saying there is no legacy hardware that would make this not work.
No.
It'll just go.
Except firewalls, which basically can exclude that there is another header. They can look into the IPv4 header, and then they see next protocol is IPv6. And if they look on this field, then they can discard the packet, of course. But a normal router, V4 router, will handle this packet perfectly normal. Yes.
I'm trying to gain in my own mind what you gain from doing that.
You gain that you can test a remote server standing at the other end of your enterprise network for V6 reachability without touching your infrastructure. Okay?
You still got a lot of work to do to convert everything to IPv6. Right?
This is not really a migration step, it's a test step where you can test certain reachability on it even goes further, but I'm run out of time. You asked too many questions. So it's your fault. The disadvantage of this, it's not nettable. It's not nettable. It cannot leave your netted network. It's an intra. That's what the name stands for, intra-site, enterprise internal. And it even works with the so-called ISOTAP router. So coming back to your question is, what you actually could start with in your enterprise. You could set up a V6 only network somewhere in your net, in test cell. And there you place V6 only servers. And if you can talk to these services, then you know that your applications running on here are V6 capable. Okay? And you can test it individually from each client without touching anything on your V4 infrastructure. That's the intention. And sorry for that, but there is another technique which is even more complex. It's called Teredo, and this technique also works over the internet. So here, remember ISOTAP intranet, Teredo is internet, because it can pass net routers with a very complex steps, and I have animated it here, but I'm running out of time. You have the trace file. What it actually does, it again forms a tunnel through the internet, and I have animated here step by step what happens, but I packed too much into it, so this is what happens, and that's the trace file, which, anyway, where is the shark at the moment? The shark, the little shark?
It's up here.
Okay, so everybody wants this trace file, it's on this, that's a technique you can easily try at home. Your provider, your home provider, must not know anything about it. It is V4 internet, and your local router must not know anything about it. So your local, the ADSL router or whatever you have, is fully only V4. What you do, you again do a tunnel from the client directly to any relays on the internet. These relays are there already, sponsored by Microsoft, called Teredo relays. And there is on the internet, there are also instructions how you enable this, and I recommend do this. You learn a lot about this. So sorry for the hurry, but I hope you still learned something, and I motivated you to go home and switch IPv6 on immediately.
Yeah.
The other slides will be available after the session.
I got a question. Aren't there some security issues with turning on IPv6?
There are a lot of security issues with turning on V6. Yes?
I got a question.
So the security issues are not solved yet.